All right, with that, let's move on. So now let's move into chapter 10, the moment of inertia. That's the title of the chapter. You have, I should have said moments, right? There's different moments of inertia. Well, this term may leave you cold, like I don't really know much of what they're talking about. It really comes down to mass moment of inertia, and that's a great lead into dynamics, the next class. But they still use the same terminology of having moments, and it's related to an area or a volume. So we're going to first work with defining it, then we'll talk about the parallel axis theorem, and then we'll talk about how to compute the moments of inertia for composite areas. So we'll do integration up here, then we'll do summation down here, and then we won't get to it today, but we'll cover next time mass moment of inertia. So what is the definition of the moment of inertia? First of all, it's a lot of times it's referred to simply just a mathematical computation. They'll say, oh, this is the first moment, and this is the second moment. Can you tell why one is called the first and one is called the second? Maybe the power on the y. Integral y dA. All right, what would be your best estimate of what A is? Area, little chunks of area. It's an area integral. What is the y? Distance measured from the x-axis. That's what it is. So if I said, here's your x, y, and here's some area out here, if this is a little chunk dA, it's that distance from the x-axis. That's what y stands for. And it changes as you move around and do that integral over the area. And then this one is y squared. It's the distance squared. All right. So you can compute about the x-axis, I sub x, that's the one we just wrote. So you have the y squared, but you can also compute it around the y-axis. So if you're coming with respect to the y-axis, what's that distance? That's x. That's the distance of that little chunk of area from the y-axis. So this is a little confusing, I know. So you'll say, okay, we're going to calculate the moment of inertia. We're just going to do it for an area, not a mass yet. We'll get to that later. And we'll do it with respect to what axis? And sometimes in 3D, they'll put XX. That's just on that XX axis going parallel to the x-axis instead of an axis that goes in the XY plane at some angle, which you can do in 3D. But this is just 2D notation. This would be 3D notation, but you'll see that double subscript on the I. Okay, so the moment of inertia, I, with respect to the x-axis, and it's equal to some area integral, the second moment area integral, the integral y squared dA. Now, I don't emphasize it. There's not going to be an exam problem on it, but you could calculate the polar moment of inertia, and actually that's a great lead-in for dynamics when things start rotating around the point O. That's what they're going to do. So Ix and Iy are used. They're used to determine the strength of structural members. You're probably going to take a solid mechanics class next, as well as rotation, moments of inertia for rotation, rotational system and dynamics. It then determine the location of the resultant pressure force on a submerged plate. If I have time, I'm going to cover that today. But that is another application where you see this math coming out. So this would be a solid mechanics class. This would be a fluid mechanics class. All right, let's do this question first. Forget this one. All right, what are the typical SI units for the first moment of the area? So is it dimensionless, meters, meter squared, meter cubed, meter to the fourth? What was that first moment of the area? Was it an integral of dA? Was it the integral of dA squared? Was it the integral of y dA or x dA, some length, or the integral of y squared dA? Of these four, another clicker question, A, B, C, or D, which of these four is the first moment of the area? All right, let's take a look at the results on that one. So the glass is perfectly correct, 100% correct. So what I'm going to do before I grade the first question is this is the first moment of the area. Now I go back and I re-ask that question in SI units. Think about, you could use millimeters, centimeters, but just think about meters, a typical length. What would be the dimensions of this integral y dA? Same question re-asked. All right, let me do this. I'm going to ask another question. So I have a coordinate system right here. This is my x, my y coordinate system. And I'm interested in calculating this integral of y dA for a strip that's very, very thin, right? Very, very thin. But that strip has some area. I'm going to say that area is 0.1 meters squared. That's how large that area is, but it's a very thin strip. And is it parallel to the x-axis or parallel to the y-axis? It's parallel to the x-axis. Okay. And we're going to say that the y is at a location of 5 meters. All right. Can you tell me what is the magnitude of the integral y dA for this problem? And this is a numeric problem, so I'm going to switch it off to numeric. No units, just give me the numeric value. What is the integral of y dA for this problem where the strip is very long and thin, has an area of 0.1 meters squared, and it has a distance, did I say this was 5 or 0.5? 5 meters away. All right, everybody's in. Let's go ahead and grade this one. So it's the area is, this is approximately the area because y doesn't change over that whole strip. It's just 5 times 0.1. Is it not? So that's 0.5. Are any other answers close? Okay, so now that we've graded that one, I'm going to go back and ask this question one more time. What are the typical SI units for the first moment of the area? Let's put it in multiple choice and away. All right, so I'm glad that we have a lot more people that are correct, although I'm a little disappointed in myself that we don't have more correct. But if you take a look, if you just followed this through, didn't that have a meter for length? And the area had meters squared. The integral y dA is going to have length cubed in SI units. Standard length is meter cubed. So isn't that the correct answer? All right, let's go back and see about this. Wasn't this one of our trials? And I think only D is correct, true? And didn't I ask that the first time? I think this is the first time. So if you've been sitting there saying, come on, it's D, come on, it's D, sorry, but I wanted to get more along the path with us, right? All right. Ready for a harder question? Maybe it's not harder. Maybe all this helps you. Okay. What are the typical SI units for area, moment of inertia? What was the equation for that one? There you go. So 100% correct. Very good. Now let's do this. Here's a new one. Insert new page. there's something called the mass moment of, I said I wouldn't get to it today, but I'm going to say that it's the integral of y squared dm. Not dA, dm. What do you think the dm, what the m in the dm stands for? Mass. True? I mean, it's the mass moment of inertia. All right. Who's really brave and can tell me what do you think the standard type of SI units for this term, this mass moment of inertia, might be? Meter squared kilogram. Meter squared kilogram. So right away, this chapter has terms which are funny. Funny because it's like, what units are these? What does this stand for? What is this used for? Something that's meter cubed, something that's meter to the fourth, something that's kilogram, meter squared, but all are relevant and very interesting and useful properties that engineers deal with. All right, so let's calculate the moment of inertia for the shaded area about the x-axis. We'll do it for the x-axis first. Here's the answer down here. This is the x-axis. About the x-axis, I measure the distance from the x-axis to that little chunk dA. That's not x, that's y, that distance squared. This is the integral I want to compute. All right, the most convenient little chunk of area for this, I know that in calculus you can go back and you start with a little dx dy, but we like to start with strips. Why do I like to start with a strip that has a height dy? Because what does it have everywhere in that strip? The same distance, y from the x-axis, right? It has the same distance, y. So let's say, okay, how big is that strip? What is the area of that strip? If its height is dy, I multiply its height by its length. Okay, I'm going to pause. I want you to tell me what I multiply this by to get dA. I'm just going to walk around. I want you to show me on your paper. What is it? It's the equation for the length of that strip. Is that strip a function? Is the length of the strip a function of the distance y up? Is it a function of y? You bet it is. So I'm glad a lot of you got it. So it's basically this length is 8 minus this distance right here, and then you just rearrange this equation to get, well, x at the lower limit of this strip, or the distant location of that strip, is a function of y. It's 1/2 y squared. So it's 8 minus 1/2 y squared. Now we're ready to do the integral. So I sub x is equal to the integral of y squared times 8 minus 1/2 y squared times dy. We integrate. What's our lower limit on y? 0. What's our upper limit on y? Upper limit on y? 4. We end stop at y equal to 4. How about I give you a minute or two to see if you can confirm that that integral is 68.3. All right, I hope enough of you are able to confirm that. Good? Very good. Now let's do it. Let's do it about the y-axis. If you do it about the y-axis, do you think you want to use a strip where y is changing, or do you want to use a strip where y isn't changing? I'm sorry, where x isn't changing. This is a strip that you're going to have that's thickness dx, and when you compute the integral, let's do the moment of inertia about for the area about the y-axis, that's the integral of x squared dA. And so what is this dA now for this strip? It's going to be dx times, what is that going to be? The height in y, the square root of 2x minus 0. They all go to 0 in y. And then you have x squared, the integral. What about the lower limit and the upper limit? And now you have it. You can compute the moment of inertia for that area about the y-axis, and that should give you 585. All right, let's press on. Well, what we're going to find is that when we get to composites, we like to build things out of very simple elements. Well, this is a pretty simple area, is it not? That last one was pretty complex. So let's do this. Let's compute the moment of inertia for that shaded rectangular area of base B and height h about the x-axis. Here we have to do it symbolically. It's not a numeric answer. And here you can see the answer down here to confirm. But I want you to set it up, show me that you set it up, and then do the math correctly. So we're asked to calculate I sub x, which is the integral of y squared dA. Maybe this is one of the times I really should go back to maybe where your calculus instructor left off, although you'll find a lot of engineers jump to summation of disk or summation of strips because of the ease at which you do it. Once you get used to it, it's a lot easier. But let's start with dx dy. It doesn't matter, okay? All right, so now we're going to integrate y squared, put a double integral. And you could put dx dy, or you can put the double integral dy dx. It doesn't matter, does it? But you just have to be consistent. These are the limits for the y, and these are the lower and upper limits for the x. So they have to match maybe for the y, and these have to match with the x. Do you want to go with side A or side B? It doesn't matter. Pick one and go for it, right? Which one do you want to go for? A? I see an A. The first A has it, so we're going to go with A. So we're going to integrate with respect to x first, and x is going to go from a lower limit of 0 to an upper limit of h or b for x. For x. H or b. It's going to be b. And then for the y, we're going to go from 0 to h. All right, so if you integrate y squared with respect to x, what do you pick up? You pick up y squared x, evaluated at 0 to b, and so that becomes y squared b minus 0. Now we have the outer integral, dy, going from 0 to h. So you're going to have b 1/3 y cubed evaluated 0 and h. You pick up 1/3 base height cubed. And so there you go, I sub x. You can do it this with version B too. Okay, so 1/3 base height cubed. Let's do this. Let's say I have a coordinate system x and y, and I have this strip. What do you mean that strip? Yeah, this is my little strip. That's my area. Well, how big is your area? Well, my area has dx for the base, and it has height h. All right. For that little strip, can you tell me what I sub x is for this little strip right here? Would it be 1/3 dx times h cubed? Would it be? Does that look okay? You know what? You can come back to this problem And now you can calculate that area moment of inertia about that x-axis using what I'll call vertical strips. So here's our little strip, right? It's like if I wanted to calculate I sub x, I would just sum over the little dix's, where the little dix's are vertical strips. And we just did that. What that little dix is, it's 1/3 base dx times height cubed. But in this case, we are, the height is what? It's a function of x. What is the height is y, which is equal to the square root of 2 times x. So it would be 2x to the 3/2, or the square root of 2x to the power 3. Did you follow? Are we doing okay? And what is our lower limit on x? 0. What's our upper limit on x? Boy, that integral sure does look a whole lot different than the previous integral. But am I going to get the same answer? And yes, you will. You'll get the same answer. So let me leave that with you to check. And now let's press forward. Sometimes they'll say, here is a very simple area. It's a rectangle, base B, height H. You could put the origin of your coordinate system down there in that lower corner. The x-axis running along the lower edge, the y-axis on the left side edge. But sometimes they'll say, can you calculate it about the centroidal x-axis? This terminology can confuse us. What do they mean by centroidal x-axis? You have a centroid. Can you guess where that centroid is located on the x? How about b over 2? How about in the y? h over 2. Isn't it? Isn't that the location of the centroid of this little area? That's pretty easy. And then you can introduce the concept of an x-axis, which is parallel to our original x-axis, going through the centroid. It's what we call the centroidal x-axis. Maybe not to confuse it with the other x-axis, you put an x prime. X prime would be, or maybe you put xc or some other notation. I think prime is the notation used in this textbook. This is the centroidal y-axis for that area, y prime. Okay, somebody says, I want you to calculate I x prime. Or sometimes they'll do it like this, Ix bar. What? What's that bar doing? That bar is emphasizing it's going through the centroid. You'll see that notation in different places. All right? But how would I calculate this integral that is the integral of y prime dA? That's y prime squared, isn't it? How would I calculate that? Do you want to do it just going back and saying, here's a little dx dy and run with it that way? I'll set it up, make it as less painful as. So y prime squared, this dx prime dy prime, what does the x prime go from? Negative b over 2 to positive b over 2. What does the y prime run from? I just should have moved that over a little more. The integral from negative h over 2 to positive h over 2. And what do you, here's the answer. Other people have done it, we've done it before, but it's 1/12 base times a height cubed. So for a little rectangle of base B, height H, the centroidal, the area moment of inertia through the centroidal x-axis is 1/12 BH cubed. Here's a question. What is Iy prime equal to? I'm going to walk around and see if you can tell me what that is without doing a whole lot of calculus, doing a little bit of an analogy in the system. All right? Let me get at least 3 people that are not on this. And so this would be 1/12 of the h, which is kind of the base or along that parallel to that axis, times b cubed. All right, maybe I should ask another here's a new question, insert new page. I'm going to have system, here's my xy coordinate system, and I'm going to put at the centroid, I have an area like this, and then the same coordinate system, but the same area too. Okay, there is another one right there. So this is area 1, and this is area 2, and they have the same magnitude. It's just one is rotated, isn't it? All right, this is our x-axis and x-axis. All right, so this is answer A or answer B, which has a larger I sub x. What is Ix? I forgot the name of Ix. Ix is area moment of inertia with respect to what axis? The x-axis, isn't it? So is it either A or B or can't be determined? Can't be determined. And so it is A. Now why is A much larger? If you look at the equation, if I get a lot of area, this is the integral of y squared dA, if I get that chunk of area far away from the x-axis, either far away in the positive sense or far away in the negative sense, but because it's going to be squared, y squared, that leads to a larger value. Versus here, it's closer to the x-axis. It's not farther away from the x-axis. So this is larger. True. Now let's move on to the parallel axis theorem. Well, the parallel axis theorem can be written a number of different ways, and we're going to only do it for an area to begin with. So parallel axis theorem for areas. For mass, the mass moment of inertia is really where you use the parallel axis theorem a lot. Okay, well, this is the way the parallel axis theorem is written on the inside jacket of your textbook. I is equal to I bar plus A d squared. All right, what do you think this is? Area moment of inertia. They left off any subscripts x or y. What does the bar on top of that I mean? Going through the centroid. It's the centroidal axis going through the centroid. And then what does the A stand for? Area. It's the area of my area, because we're doing the parallel axis theorem for areas. And D, the hard one. D. Distance. It's a perpendicular separation distance between the centroidal axis and this one is the area moment of inertia for an axis that's not there, but it's separated away from the centroidal axis by distance d. So often we'll have a very general shape like this, and you say, here's the centroid, here is our centroidal x-axis, and we're really interested in what is that area moment of inertia around the other x-axis. Let's say this x-axis down here. Well, the way you would calculate it, you'd say, first, let me calculate the area moment of inertia for the centroidal x-axis, get the area, multiply by that distance, separation distance squared, and there you go. That is it. We haven't derived it. We're going to derive it in a second. This is the way it's written in chapter 10. They're saying, oh, for this x-axis, they'll have about that x-axis is equal to, and this is kind of confusing, x prime without the bar on top. That would have been enough to say, oh, that's the moment about the centroidal x-axis. But then they seem to me double emphasize. It's like shouting. Anyway, it's really emphasizing what this term is. And then you have that area, and now they emphasize, oh, this is the distance of separation in the y between the two x-axes. Can you guess what it is for I sub y is equal to I y prime? Okay, put the bar if you want to double emphasize it, plus the same area, distance between the two axes in the x squared. Well, let's go ahead and now derive that parallel axis theorem for an area. First of all, I think it's easiest if you introduce a coordinate system and play with some coordinate system for a minute. And in this coordinate system, in this very generic area, I can actually talk about locations of points. Here, I put in numbers, 10 and 12. That's point right there. Let's say that's where my center of the area, the centroid is for this area, at location 10, 12. I just made it up. All right? All right. So we continue on and we say, you know, there's another point that's not at the centroid. Maybe it's at the location 12, 9. That makes sense. Some red point. I think I color-coded it red. And now I introduce a x prime, y prime coordinate system. What's the prime mean? Its origin is at the centroid. And it's parallel with the original x and parallel with the y-axis. So that's our centroidal x-axis, centroidal y-axis. Now, the question is I can describe the location of the centroid in this new coordinate system. It's almost too boring. The point 10, 12 in the original coordinate system is now at the point 0, 0. The centroid's at the location 0, 0 of my new coordinate system, my centroidal coordinate system. But how about this, a little bit of math that says, oh, you used to be at 12, 9. You are now at 2, negative 3. True? All right, let's play a game to see if you're following along. Let's say I'm at 5, 15. That's my location in the xy, 5, 15. I'm going to walk around. I want you to give me its location in the centroidal coordinate system. All right, so in general, we have a number of things which can be very confusing. We have x and y, and you think, oh, that's the location. That helps me identify where we're at. And then we have x prime and y prime. Oh, that helps me identify where we're at with respect to a different coordinate system, the centroidal coordinate system, instead of the other coordinate system. And then we have xc and yc. What is xc and yc? That's actually xc for this, whoops, that's yc, isn't it? Yc for this problem is 12, and xc for this problem is 10. What do we mean by xc and yc? That's the location of the origin in the global coordinate system. Can you write an equation relating the 3 x's and then an equation relating the 3 y's? Like somebody says, oh, I think x is equal to x prime plus xc. No, I think x prime is equal to xc plus x. No, I think x prime plus x is equal to xc. See what I'm doing? Because if you can do that, we have the parallel axis theorem derivation done, really. But you've got to be able to do this. So help me relate the x's. And then the similar equation for the y's. What is the equation for the y's? Maybe I make a clicker question. Okay, I'm making this up, but let's do this one. X is equal to x prime plus xc. Or I'll take this equation and rearrange it. So x is always on that side. It's x prime minus xc. Or I'll rearrange that one. X is equal to x prime, whoops, xc minus x prime. Which of these are correct? A, B, or C? I'm going to go ahead and do multiple choice and start. Oh, okay. I'll tell you what. I'm sorry, but I'm going to re-ask that question, okay? Let's do this. I didn't get in time to click it. Otherwise, I would have. Let's do this. Let's say, for this example up here, for this point right here, the blue point, okay? For the blue point, what was x equal to? 5. Was it not? What is xc for this area, for this problem? 10. All right. What is x prime for that blue point? -5, right? So, if I take a look, to move, this point works in one of those three equations, does it not? Does it not? And it doesn't work in the other two because they're not consistent. They're not the same equation. So now I'm going to ask the same question, and you can check it by plugging in numbers. Equation A, B, or C is correct. And what happened there? I had everybody correct for a while. Somebody did a last-minute switch. They second-guessed themselves. So that's the right equation. This is the right equation, and you can verify it with a few of those points. I just picked one of the points to verify it, but you can pick a lot of different points and verify it again and again. So in the interest of moving forward, I think what you can do is you can write a simple equation that for, let's say, y is equal to y prime plus y sub c. Or you could do it for the x. Both of those equations are consistent. But what I'm going to do is I'm going to say I sub x, by definition, is the integral of y squared dA. That's a good starting point for the derivation of the parallel axis theorem for areas. Do we agree that works? Now guess what we're going to substitute for y? We're going to put the integral of y prime plus y sub c squared dA. We expand, just like a plus b quantity squared is a squared plus 2ab plus b squared. You get the integral of y prime quantity squared dA plus the integral of 2y prime yc dA plus the integral of y sub c squared dA equal. Now, some of these three y's, one of those three y's is a constant for this area. As I move around little different dA's, little dA over here, little dA over there, one of those y's isn't changing. Okay, so which one is a constant? Is this a constant? Answer A. This a constant? Answer B. Or this a constant? Answer C. Multiple choice. Very good. Y sub c, the location, the y location of the centroid of that area is not changing as I'm doing this integration. It's a constant. Okay, can I then pull this y sub c outside of that integral? It's a constant. Can I pull that constant squared outside of that integral? Sure. And so what we have is this is y sub c squared times the area. All right, I'll have y sub c, I can pull the 2 out also. We have the integral of y prime dA. And then we have the integral of y prime squared dA. That's equal to the integral of y squared dA from above, which is the I sub x. All right, what do you think this term is equal to? I sub x prime. What do you mean? It's that area moment of inertia for the centroidal x-axis, isn't it? All right, this is my separation distance squared times my area. What was the separation distance? Well, isn't this distance equal to y sub c? Yeah, the perpendicular or separation distance, those two parallel axes. What does this term have to equal? Okay, why is it equal to 0? Is because 2 is 0? No. Y sub c is 0? No. This integral must be equal to 0. Why is the integral of y prime dA equal to 0? Isn't that how you calculate the centroid of an area? How do I calculate the centroid? Let's say y sub c is equal to 1 over a integral of dA only, or y dA, the previous chapter. And so in the centroidal axis, if I put, I'm doing it with respect to the y, then with respect to this y prime, there's the new origin, it's 0. So that's why this is 0. And there you go. There is our parallel axis theorem derived. Let's press forward. Well, we can use that parallel axis theorem when, especially, we compute the moments of inertia for composite areas. We're going to basically add up, this is a rectangle, and we'll have to shift it from the centroidal to a new axis. We'll sum up those, just like we did when we did the centroids. We will look for symmetry and exploit it when possible. We'll organize our calculations in the table, just like in Chapter 9. And we can treat holes or missing parts. What they'll have is negative moments of inertia. Not negative areas this time, just be careful here, but it's the negative moment of inertia. Let's solve some problems. Here is a beam, and it's a simple T-beam or cross-section of it. And we want to calculate the moment of inertia of that cross-sectional area about the y-axis. So here's our y-axis. So are we interested in calculating I sub x or I sub y? What are they asking us to calculate, Ix or Iy? I is for that moment of inertia of that area, but which one is it? Yeah, it's Iy. So we're going to calculate Iy, which is the integral x squared dA. And we look at it and we say, you know what? This is really a composite of this plus this. Let's call that 1. Let's call that 2. All right. Where is the centroid of area 1? Right here, meaning it's at a location of x equal to 0 and y equal to 25 divided by 2 centimeters? Yeah. What's the centroidal location of area 2? Well, isn't that at location x equal to 0? Y is 25 plus 5 divided by 2. That'll be 27.5 centimeters. We're going to treat this as a summation of I sub for area 1 plus I sub y area 2. Put it in a table. The number for our area, just 1 and 2. What is the area for each of those? We're working in centimeters squared. It's 5 times 25. And I'm just going to show the math. 125 centimeters squared. How about for area 2? 30 times 5. That's 150 centimeters squared. We don't even need a parallel axis theorem because it goes right through the centroid of each of those. And so what is going to be the I sub y, which is actually the same as I sub y prime for each of these areas? Is it the formula 1/12 base times height cubed? And for this area right here, the first area, what would be the base? Is it 25 for the base? And then the height 5 cubed? Don't disengage. Keep up with me. Is that right or wrong? right? Is this correct or incorrect? Looks okay? That gives us a number of 11,250. And then we'll do the 112. What's our base? It's going to be a 5, is 30 cubed. I'm sorry? Oh, that's why I'm messing it up. My notes, I reordered them. There you go. So this is 11,250. Thank you. And then this one is 260.4. And when you sum them, you get I sub y is equal to 11,510 centimeters to the fourth. If you rub that out to 3 significant digits, you'll drop that and put a 0 there. Right? Okay, thank you very much. So there you go. You now say for the same cross section, do it about the x-axis. Well, where's the x-axis? Right down here. Where's our centroid? Here and here. You're going to have to use parallel axis theorem to move from the centroidal x-axis for both of those. We're calculating I sub x. We have how many areas? 1 and 2. Let's go ahead and get the area of each in centimeters squared. We did that before. It's 125 and 150. And then y sub c is a location of the centroid in centimeters. 12.5 and 27.5. We did that before, although we didn't use it. And then what we have is we have a column for I x prime centimeters to the fourth. What is that? That's through the centroidal x-axis. So it's our 1/3 our base times height cubed. It's respect to this horizontal axis. So for the first area, 1, our base is 5, and our height, I just covered it up, is 25 cubed. That gives a value of 6510.4. Then we come up here, and we have for the second area, this is area number 2, we have 1/12 base times the height 5 cubed. That gives a 312.5. But we have to compute it with respect to the x-axis, which is we use the parallel axis theorem and have that separation distance times the squared times the area. Yes. Yes.
Oh yeah. Where it says 1/3, it's supposed to be
1/12. You're right. Sorry.
Could you just leave it as a third and then it's already...
Yes, you can. You're right. You're one step ahead. But you're fine. Because it is a 1/12. All right. So let's go with 6510.4 plus that distance, 12.5 squared times the area, 125. And I'm going to rub this out. This is my area 1 there. And you get that this is 26,042. And as already pointed out, that's the same answer as the 1/3 base height cubed, because that does share the edge, that first area. But you have to use the parallel definitely for the second one. So both of those are consistent. Let's do the second one. So what we have is we're going to have 312.5 plus the separation distance of 27.5 squared times the area of 150. And this turns out to be quite a large number, 113,750. So when we add that column up, you pick up 139,800. So I sub x is 1.40 times 10 to the 5th centimeters to the 4th. Determine the moment of the area about the x-axis. Well, this is our x-axis. And as you see it, it looks like this is a composite of 3. 1, which is a complete solid area, rectangular area. minus a triangular area minus a whole round area. So let's go ahead and go through that one. So what we'll do is we'll calculate from the first, the second, and the third. What we want is area, and then we'll get y sub c in centimeters, and this area was in centimeters squared. So the area for the first is 30 times 35. Here's 35, and here's 30. And so you pick up 1050 centimeters squared. The rectangle is 1/2 15 times 30, and that picks up 225. And then the whole is pi r squared. R is 7.5 squared, and you pick up 176.7 something. All right. What is the location of the centroid of each of those? 15, 20, and 15. We haven't used any negatives on areas or locations. We're going to use a negative when we get to the eyes to take it out, to subtract it. All right, so we calculate the ice of x prime in units of centimeters to the fourth. And in the interest of time, I'll just give it to you. You can check 78,750. What was that? 1/12 base height cubed. You could have also done the 1/3 base height cubed and not have to use the parallel axis theorem, but I chose to go ahead and use it I sub x with the parallel axis theorem, and it comes in at 315,000. This is centimeters to the fourth. All right. It's down 1/3 or up 2/3, over 1/3 or over 2/3, right? That's a centroid for triangle. You can go one of the covers that I gave you. There it is for the triangle. And what is that equation for I sub x? 136 times the base times that height cubed. So for about this x centroidal x-axis, you pick up 136. What is the base? 15 centimeters. What is our height? It's 30 centimeters cubed. So 136, 15, 30 cubed. You come in with I sub x prime of 11,250 for the triangle. No negative sign yet. All right. How about for the centroid of the whole? That's easy. But what is the centroidal, the moment of inertia about the centroidal axis for a disk? Well, that's actually given to, let me write it over here, it's 1/4 pi r to the fourth power. I'm not going to repeat it, but it's there. And so you put in and you pick out 2,485. You use the parallel axis theorem to shift it, and you pick up 101,250, as well as a parallel axis theorem of 42,246. At this point, you want to subtract those from the summation to get the total of 171,500 centimeters to the fourth is I sub x, the moment of inertia about the x-axis. I know that's the 4 significant digits. You can round it off to 1.72 times 10 to the fifth centimeters to the fourth, if you like. So we can handle composites. We've covered the definition, the parallel axis theorem, which is used a lot in the computing of composite areas when you're shifting areas further away to a common axis.